Welcome to this video supplement involving function transformations. We are going to look at two examples where we are given a graph of a function, in this case the graph of y equals f of x, and we want to draw the result after we transform that graph. So the first thing we're going to do is write out the transformations involved. In this problem, the negative 2 out front means that we have a vertical stretch of 2. The negative means that it's reflecting across the x-axis. Inside the function, the x minus 3 means that we're moving it to the right 3, and the plus 1 outside of the function means that we're moving the graph up 1. Those are the transformations that we will put the points on the graph through in order to get the new graph. In doing that, we will take an endpoint, or each of the endpoints of pieces of the original graph in order to find out where the new graph goes. So in this example, we are going to take 4 points and go through the process with them. Here's our first point. It's already down 3. Well, we're vertically stretching at 2, so it'll go down 6, 4, 5, 6. But then we're reflecting it across the x-axis. So instead of being down 6, it's going to go up 1, 2, 3, 4, 5, 6. And there's where the point would end up after the vertical stretch and the reflection. But we still have to move it to the right 3 and up 1. So there is ultimately where that first point would wind up. Second point, the one in red on our graph, it's up 1. We'll vertically stretch it 2, so it goes up 2. And then we're reflecting it across the x-axis. So instead of being up 2, it'll be down 2. After we've vertically stretched it and reflected it across the x-axis, we need to move it to the right 3 and up 1. The next point, vertically stretch it 2. So instead of being up 1, it'll be up 2. But then we're reflecting it across the x-axis. So instead of being up 2, it'll be down 2. And then we're moving it to the right 3 and up 1. And our final point, vertically stretch it 2, we'll put it up 4. Reflect it across the x-axis, puts it down 4. And then we're moving it to the right 3 and up 1. Last but not least, we need to connect those dots in the proper order to get what the new graph looks like. So we start up here at the first point, connect it to the second point, the red one, then connect that over here to the magenta point, and last but not least, connecting it down to that final point. That would be the new graph for the transformed function y is equal to negative 2 f of x minus 3 plus 1. Let's consider our second and final example. Again, we're given an original graph of y equals f of x. Before we can write out the transformations on this one, we need to modify the inside of the function. In other words, we need in parentheses just an x and something. In order to get that, we have to factor out a negative 1/2 on this problem. If we factor out a negative 1/2, that really means that we're going to be dividing the 2 by negative 1/2. And when we divide by a fraction, that's the same as multiplying by its reciprocal. So the number that will go inside with the x will be a minus 4. The other way we can check that is if we distribute the negative 1/2 to the negative 4. Negative 1/2 times negative 4 is a positive 2. We still have the minus 3 outside of our function. Now, because that multiple is inside the function, it's going to be a horizontal stretch. And remember that the horizontal stretch is always the reciprocal of that number inside the function. So in this case, we have a horizontal stretch of 2. And because of the negative, we're reflecting it across the y-axis. And then we're moving it to the right 4 and down 3. So here are the transformations that we'll use, and let's go to our graph. We will take the endpoints of each portion of that piecewise function, Although we're not really writing out the algebra for the function, it is on some level a piecewise function at least. And we're going to put each of those points through those transformations one at a time. So let's start with this point in blue. We're horizontally stretching it 2. So instead of being to the left 1, it'll be to the left 2. But then we're reflecting it across the y-axis. So instead of being to the left 2, it'll be to the right 2. Then we're moving it to the right 4 and down 3. Here's where that point would end up. Let's take our second point. Horizontal stretch of 2. Oh, it's at an x value of 0. 0 times 2 is still 0. Reflected across the y-axis, it's on the y-axis. That doesn't change anything. So then we're going to the right 4 and down 3. Next point, the magenta point, it's to the right 2. When we double that, because of the horizontal stretch of 2, it'll be to the right 4. But then we're reflecting it across the y-axis, so instead of being to the right 4, it'll be to the left 4. But then we have to move it right 4 and down 3. So there's where the magenta point ends up. And finally, this point here in purple, it's to the right 3. We're doubling it, so it'll go to the right 6. Reflected across the y-axis, so it's going to go to the left 6. If it ever falls off the grid, we can just add a grid mark. Then we're moving it to the right 4. 1, 2, 3, 4, and down 3. And now we will draw the resulting graph. Starting at the blue point, then we went to the red point, then we went to the magenta, and finally, we go to the purple. And that should be how the graph ends up. Now, one item worth noting here, this portion on the new graph is 2 units long. The corresponding piece on the original graph was 1 unit long, and that makes sense because we horizontally stretched the graph by 2. So comparing little pieces of the graph should let us see whether we've transformed correctly if we want to double check. But keeping that in mind, really, all we have to do is the following. Rewrite the function if applicable so that inside the function we have just an x in parentheses. Write out the transformations that will be used, and then put each endpoint, or like maximum or minimum point of the original graph, through those transformations in order to draw the resulting graph.